All right, great. Thank you very much, Svi, for that nice introduction. Okay. So I'm going to try to give you an overview of the transient science that the SWIFT satellite has conducted in the last 14 years or so. And then we'll be hearing, in much more detail on almost all of these subjects over the course of the rest of the week. But before I begin, as Svi mentioned, I wanted to make sure that all of you had heard that a little over a month ago, NASA renamed the SWIFT satellite in honor of the former principal investigator and really sort of driving force behind SWIFT, Neil Gehrels. And so now it's known as the Neil Gehrels SWIFT Observatory. Previously, it was the SWIFT Gamma Ray Burst mission. So not only is this meant to honor Neil, but also to reflect the sort of diverse science that SWIFT is doing here. But I wanted to just really thank the organizers on behalf of everyone on the SWIFT team. It's a real honor to be here and have an opportunity to give this talk. So thank you very much for having me. Rather than just kind of going through point by point and talking about the science that SWIFT has done, I thought it would be at least interesting and perhaps even a little bit of fun if we could sort of go back in a time machine and look at the original proposal that was submitted for the SWIFT mission. So on the way over here, I actually did this. I managed to dig it up. This is the cover sheet, actually not from the original proposal, but from the Phase A study report. It was originally submitted in 1998. Hopefully everyone in this room was actually alive at that time. But I thought what we could do is go through what science SWIFT was initially designed to do, what the sort of metrics for success that it originally had. We can compare that with what it actually did and see if we can learn kind of any lessons, for future missions going forward when we think about that as well. So here's a summary slide from 1999 that's supposed to summarize the field of gamma ray bursts at the time. And I think there are actually pretty poignant analogies you can make here with what's going on in the world of gravitational waves right now. At the time, gamma ray bursts were an extremely new frontier. A number had been detected, but it was only in 1997 that the first were localized. We could identify their counterparts at long wavelengths, their host galaxies, measure their redshifts. And so this is the table of the dozen or so GRBs that were known at the time that the SWIFT proposal was submitted. Back then, individual phone numbers, 970228, 980425, 990123. You could actually remember these telephone numbers. These are named after the UT dates on which these were discovered. And this was kind of the state of the art of what their afterglows looked like. So this is a plot of two X-ray afterglows. So you're looking at flux as a function of time. You get the early sort of prompt emission initially, come back a few hours later, get a few points on the tail as it's decaying. It fits like a power law. That's not extremely surprising when you only have 2 or 3 points. You can fit a power law to it. And so in this context, the SWIFT mission was proposed, as a number of other missions were actually proposed. And these are the science questions that SWIFT was designed to answer. What are the sites and natures of gamma ray burst progenitors? Are there multiple classes of bursts? What is the local environment near the burst? And what can GRBs tell us about the early universe? Now, it turns out that this field was so quickly moving that actually some of these questions were actually answered before SWIFT was launched, but that's okay. A number of them we sort of built upon the work that was done before they launched. A number of them, we sort of have tackled on our own. And the instrument and sort of observatory that was built to do this was supposed to have these characteristics. So rapid multi-wavelength identification of the afterglow, good prompt localization, claimed we could detect about 300 GRBs a year. Turns out we were off by a factor of 3 or 4, but what's a factor of 3 or 4 amongst astronomers? X-ray afterglows and optical UV afterglows starting at 50 seconds, spectroscopy across the sort of full X-ray bandpass, redshift determinations. As we'll see, that one didn't turn out quite so well, but that's okay. And some ancillary science, rapid hard X-ray survey, rapid multi-wavelength studies of SGRs. So how do we actually do when we compare the science that SWIFT was designed to do to the science that it actually did? So let's go through the sort of gamma ray burst results. I think the biggest legacy of SWIFT, certainly in the gamma ray burst era, will be in the study of short gamma ray bursts. Well before SWIFT was launched, it was realized that gamma ray bursts came in at least 2 flavors. Those with durations of less than 2 seconds were known as the short gamma ray burst. Those with durations of longer than roughly 2 seconds, creatively named the long gamma ray bursts. Long gamma ray bursts were tied to the core collapse of a massive star, stellar explosions, prior to SWIFT launch. But until the launch of SWIFT, we did not have any precise localizations, any afterglows for the short GRB class. And so in 2005, the first afterglow detection for a short gamma ray burst, it was a mere 11 X-ray photons. You could count them, name them, make a fancy spectrum out of them if you wanted to. But just from this few arc-second position for the first time, we could actually pinpoint the location to identify the galaxy that this explosion went off in. And this galaxy right here, the redshift of 0.225, is completely unlike any of the galaxies in which long GRBs went off. It's a massive elliptical, it's in the middle of a cluster, has no ongoing star formation, and that immediately pointed to a very different origin than we see from long GRBs. And since that time, SWIFT has been detecting a little less than 10 short GRBs every year. We now have a sample about 100 of them. And with those samples, you can do pretty powerful population studies, in particular of the host galaxies in which they explode and the environments of these within these host galaxies. So the host galaxies turn out to be a mix of star forming, actively forming new stars, and elliptical galaxies. The fact that you see a significant fraction in these elliptical galaxies with no ongoing star formation tells you that you must have some kind of long-lived progenitor system. Doesn't tell you what that progenitor system is, but it can't be a massive star because they don't live long enough. They don't travel long distances. But perhaps the most interesting clue to what these explosions could be came from their locations within their host galaxy. And this is a plot of the projected physical offset of these explosions. So the distance from the center of the galaxy in which they exploded, measured in units of kiloparsecs as a cumulative histogram. So if you look first at the black line, you see the long gamma ray bursts. They're typically found within a kiloparsec or so of the center of the galaxy which they exploded. This is what you would expect for massive stars. They're formed in the disks of galaxies. They don't have time to migrate away from there. But short gamma ray bursts, which are shown as the red line, are found at much larger distances. A typical distance of order something like 5 kiloparsecs, and there's a distant tail out here that can extend out to 10s, 20, maybe even like 50 kiloparsecs. This is well outside the typical disk of a galaxy. This is not where you're forming massive stars. And again, this points to these long-lived progenitor systems. And in fact, it provides a reasonable match to binary stellar population synthesis models for binary neutron star mergers. So this is some of the best indirect evidence that we've had that short gamma ray bursts were tied to binary neutron star mergers prior to this recent discovery of gravitational waves a few months ago. In addition to these sort of indirect evidence, SWIFT and observers in ground and in space have been looking for what Svi mentioned as this kilonova emission. So when 2 neutron stars merge, some of the neutron-rich material will be dynamically ejected from the system. That dynamically ejected material will undergo nucleosynthesis, and because it's so neutron-rich, you expect that to produce R-process elements, and those R-process elements will then radiate away to give you a transient source that should last for of order a few days, maybe a week, and will likely be quite red because you have these very heavy elements that have very high opacities in them. We'll hear a lot about this going on. I'll only mention it very briefly. But with SWIFT, what we've been doing is looking for these late-time red bumps on timescales of like a week after the burst, after the afterglow emission, which is very bright from this collimated jet pointing along our sight, fades away. You can see here that in the red filters, it's only a handful of points, but it seems to be fading away. In the optical filters, it's certainly fading away quickly after only a few days. But then there's this bump after a week that may be consistent, this kind of kilonova-like signature. And so this is something we're continuing to do with SWIFT and provided really this sort of tantalizing evidence that these kilonova where heavy R process elements were formed actually did exist in the universe. Now, of course, we made a revolutionary leap forward just a few months ago with the direct detection by the LIGO Observatory in Virgo of gravitational wave signal from the merger of two neutron stars. And just 2 seconds later, from the gamma ray burst monitor on Fermi, the detection of a short gamma ray burst. So we don't have any audio for this, so I can't do that, but I'll play the movie anyway. So you can see the period chirp sort of increasing here as these two neutron stars approach each other. Coalescence right here. 2 seconds later, a 2-second long gamma ray burst that looks like, at least in the detector plane, sort of all the other short gamma ray bursts that Fermi sees. Now, it turns out that because it's so nearby, it's extremely subluminous, several orders of magnitude less luminous than any other short gamma ray burst for which we have a distance measurement. Understanding why that is, does that have something to do with our geometry? Does it have something to do with the mechanism by which the gamma rays were created? Is something I think you're going to hear a lot about in the upcoming talks this week. And so unfortunately, this location was blocked by the Earth at the time of this merger. Swift was sitting behind the Earth and couldn't see that location, and so we could not detect the gamma ray signal. But what we could do, because we have this promptly slewing spacecraft, is immediately start following up. First, the Fermi GBM localization. Then, as that was subsequently refined based on the LIGO Virgo localization to about 30 square degrees. Then, as the optical counterpart was identified from Chile down to only a few arc seconds. And we were able to respond quite quickly and detect this relatively rapidly fading ultraviolet emission, which is shown here. This is something that was perhaps not as universally expected as this kind of week-long red kilonova signal that I was talking about before. Again, I think we'll hear a lot more about what is the origin of this early blue UV component. Are we seeing some R-process nucleosynthesis that is perhaps not generating as many heavy elements? Are we seeing some kind of shock cooling emission from a cocoon? A variety of different explanations for what that could be. But this really watershed event has shown, I think, the power of what's to come for a multi-messenger astronomy going forward. So that's the sort of story for short gamma ray bursts leading up to this time. As I said before, prior to the launch of SWIFT, we had quite compelling evidence that long gamma ray bursts resulted from the core collapse of a single, very massive star. But these explosions can be extremely luminous. And so it's long been held out that because they're so bright, it might provide a powerful way for us to study the very early universe. In particular, if one of these objects goes off in a galaxy at, let's say, a redshift of 7, 8, 9, 10, when we are reasonably confident that galaxies had formed, that massive star formation was ongoing at that time, you can use their bright afterglows as a backlight to study the ISM in the host galaxy and the intergalactic medium along the line of sight, and in particular, to measure the neutral hydrogen fraction. So we think that around a redshift of 7, 8, 9, 10, this was when the universe was undergoing this phase transition known as reionization. And so what we would like to do is use them to probe the neutral hydrogen fraction during this epoch at which it's very hard to study other galaxies. In particular, gamma ray burst afterglows can be many, many orders of magnitude more luminous. Of course, they don't last for very long, but they can be much more luminous. We can also use these as a tracer of star formation. All you need is a single massive star to get a gamma ray burst, we think, maybe in a binary system, but not more complicated than that. And so if we look at the rate at which gamma ray bursts go off as a function of redshift, this should tell us something about the rate of star formation in the universe as a function of redshift. And it's a very independent technique to other people who are looking at UV flux from galaxies, at submillimeter flux from galaxies, and a variety of other techniques to measure the rate of star formation. So there's a nice single example of this from a gamma ray burst that was detected in 2014, where you're measuring the effective depth to the Gunn-Peterson trough in the Lyman alpha here from this event. It was detected at a redshift of 6.3 or so. And you can see that there's a lower limit on the effective depth here. And you can translate that to an upper limit on the neutral hydrogen fraction at this redshift. And you can see only with a couple of gamma ray bursts, we're starting to probe interesting upper limits on what the neutral hydrogen fraction was at these redshifts where we think that reionization is going on. So we're continuing to try to do this, finding these sort of rare events that are out at redshift 6, 7. Really, we want to go to 7, 8, 9, maybe even 10. That might be a little overly optimistic. But getting moderate resolution spectra of these sources is one of the high priority objectives for the mission still going forward. For the most nearby events, it had, as I said, it had been established that they were powered by the core collapse of most massive stars. And that's really coming from the handful of events that we can see in the very nearby universe. The reason for this is because they're nearby enough that after the afterglow emission fades, after a few days, we can continue to observe the source, and we actually see evidence in the optical spectra for broad features that look like other core collapse supernovae that we see. And so studying these rare nearby events has allowed us to look at them in even more detail. This is an example from 2006 of where we saw this sort of thermal emission at X-ray wavelengths that lasted about 10,000 seconds long that we think is from this sort of shock breakout of actually, or the shock cooling signature here at ultraviolet wavelengths of the star. Now the duration is quite longer than you might normally think of for a shock breakout signature. The time scale of this is set by the physical size of the source through which the shock is breaking out. And so we think what might have been happening here is that this is a star that had some mass loss episode prior to its explosion, and seeing the shock actually, we're not seeing the shock break out from the stellar envelope because that would be much more short-lived, but we're seeing the shock break out through this dense material that was surrounding the star immediately prior to its explosion. And there you can see the X-ray signature from that. After that fades away, you get this more typical power law afterglow signature. And you can see this in the ultraviolet, where you see this cooling emission that's only seen for sort of the first day or so after the explosion. And then after that, you see the more typical radioactive elements that are synthesized from the supernova. Coming back to this question of how many classes are there of gamma ray bursts? As I said before, it was pretty well established from the BATSI era. This is a histogram shown in black of the duration of the prompt emission, that there were two classes of these events. These are the short ones with durations less than a few seconds or so. These are the long ones with durations of tens up to sort of hundreds of seconds. But one of the interesting things that Swift has discovered over the last few years is that there's this tail of events out here of very long durations. So instead of prompt emission of 10 or 100 seconds, we see these central engines that are on for timescales of 10,000 seconds. In one case, which I'll talk about later, even longer than that. And these have comparable isotropic energies. We can measure the redshift in a few of these cases. They have comparable isotropic energies to the long duration gamma ray bursts, these core collapse of massive stars. But we really don't know necessarily what is powering them. You can imagine if you have a much longer time scale. For the long GRBs, the time scale we think is kind of set by the free fall time from the envelope of the star to fall onto the black hole that's presumably formed after the core collapse. So you have a very long duration. You might need a sort of very radially extended star, if that's what you want to use to power that. It's not obvious how those would explode, how they might give you jets in which you would give gamma rays. So there are a variety of other models that have suggested what may be going on here. Late time color evolution of the sort of long-lived counterparts of these events suggests maybe that you're seeing supernova in them, but we don't see the kind of broad features that we see in other supernovae. So I would say this is still a real open question as to what is powering what we now call the ultra-long gamma ray burst. Again, very creative name we astronomers are with these things.
Excuse me.
Yes?
How many events have you observed? I saw the probability, but not the overall number.
So the overall number of ultra-long gamma ray bursts now is somewhere between 4 and 6, depending on what exactly you call them. The reason why the number of these events is detected is so low is because Swift is in a low Earth orbit. So it orbits every 90 minutes or so. And the duration of these things, 10,000 seconds, tens of thousands of seconds, is actually comparable to the orbital time. And so it's very hard for SWIFT to detect things that are on sort of those kind of time scales. So actually the rate of these events could be significantly higher than we're sensitive to, but we don't know because of the orbit that we're in. Any other questions at this point? Please feel free to raise your hand. I'll try and call on people as we go through here. And then in terms of these other classes of GRBs, over the 14-year duration of the SWIFT mission, there have now been a handful of events. The two most prominent ones were actually discovered back in 2006, but we've seen a few of them since then, where the duration is longer than a few seconds. And so we would normally call these long duration gamma ray bursts. But despite being relatively nearby, there are no supernova associated with them to very deep limits. So we now have, like I said, about a half dozen of these events. Typically, the limits are not quite as good as the two from 2000, but they're still relatively constraining in terms of the supernova that are associated with these. Here's one example where you can see the optical light curve from there's one of these GRBs in 2006. You can see the optical light curve peaked on a time scale of about a day and then faded away. And then on a time scale of about 2 weeks, where you normally see this bright supernova emission. This is from supernova 1998 BW, which is sort of the typical, or maybe it's slightly brighter than average, but not dramatically so, supernova that's associated with the GRB. And here are our limits several orders of magnitude below that. So it's not like this line of sight is extremely extincted. We see the optical afterglow. We can measure the colors. It's not like dust is in our way. It really is that these GRBs don't seem to produce supernovae. Now, why that is, I don't know. The classification of some of these events is still somewhat controversial. It could be that this is actually a short burst from which we're seeing extended emission. It's kind of a misnomer. That sounds a lot like a long burst to me, but that's okay. We don't have a great answer for this yet. And the final thing I want to mention from GRBs is afterglow physics. You saw before when I showed the X-ray light curve that was sort of state of the art prior to the launch of SWIFT, which just had only a handful of points in it. And now with this prompt response and sensitive narrow field X-ray telescope on board, we have thousands of X-ray light curves that are sampled with this sort of exquisite sampling. And rather than seeing just this very simple power law behavior, it's not entirely surprising. We see a much more complex phenomenology. We see typically very rapid decays at early times. You can sometimes see bright flares that have comparable emission to what is actually emitted in the prompt emission from these GRBs, plateau phases with relatively flat decays, then power laws kicking in. There are a variety of explanations for all of these, but I would say it's still somewhat of an open question as to how do you get these flares, what is powering these plateaus, what is the sort of origin of the sharp decay phase. But this is sort of one of the really sort of best data sets we have for GRBs coming from SWIFT. So I think if I want to summarize in terms of gamma ray burst science, where does SWIFT stand? We'll look at the report card. So what are the sites and nature of GRB progenitors? I think we've done very well on this front. We knew that long GRBs were formed from massive stars. We now know that short GRBs, at least some, have some connection to binary neutron star mergers through a variety of lines of evidence. We still have this open question of why was this one short GRB so subluminous? Is it the same thing as what we're seeing with SWIFT? But I think we've made a tremendous amount of progress here. Are there multiple classes of bursts? The answer to this is clearly yes. We knew that the answer to this was yes prior to the launch of SWIFT, but now we know that there are actually even more exotic phenomena that we didn't know before. What is the local environment near the burst? I didn't show too much of the sort of host galaxy studies, but we have these very nice high-resolution optical spectra where we can probe the ISM in these distant galaxies with exquisite precision. What can GRBs tell us about the early universe? I think we made a lot of progress here, but we haven't really answered the fundamental question of, what are the sites and when did cosmic reionization happen? That's an ambitious goal, but it's something that I don't think we've done so far. And in terms of what we provided, I think we sort of met most of these benchmarks. The 300 GRBs a year was definitely somewhat of an overestimate. We're down around 80 or 90, okay? You have to extrapolate the luminosity function down to lower levels, so there's some uncertainty there. There's probably a little bit of overselling going on as well. You want your mission to sound as compelling as possible. And redshift determinations. This is something that we've really only been able to do for a handful of events from on Swift. We really rely on ground-based observers to do this. But everything else I think we've met, and so it's been, just in terms of gamma ray burst science, I would say a remarkably successful mission. So then in addition to gamma ray bursts, there's roughly a few paragraphs in the proposal that are dedicated to what's called additional science. And 4 things are kind of called out on this. One is the BAT survey, which is the most sensitive all-sky survey at hard X-ray wavelengths. I won't talk about that because it's not too much in the transient science, but there are some nice catalogs, highly cited, and papers looking at spectra of these sources. There's some discussion of CFER2s, mostly coming from the BAT survey, so I'll skim over that briefly. Soft gamma ray repeaters. These are from highly magnetized massive stars that have sort of dipole magnetic fields of something like 10 to the 14, 10 to the 15 Gauss that undergo these dramatic outbursts. I'll show you a really prominent example of that. And then everything else that Swift was sort of dedicated to is just called rapid reaction science. And it's 1 paragraph in the proposal. And there's really just sort of 1 sentence at the end here. As with any new observational capability, the potential for serendipitous science return is high. So this 1 sentence on the proposal is honestly what we spend more than 50% of our observing time doing right now with this satellite. So I think that has some sort of interesting lessons that we want to draw as we go forward. But what I want to do is just sort of briefly summarize some of this additional science that Swift is doing that I know other people will be talking about in more detail. So really, about a month after launch, in 2004 December, one of the known soft gamma ray repeaters, SGR 1806-20, went off and had the most remarkable, I think they're called hypergiant or super flares. I don't remember. Part giant flares, Carissa? Pure giant. OK. Just giant flares. You can't actually see how dramatic this is because the peak is not shown here because it saturated Swift and essentially all other gamma ray detectors that we're observing at the time. The only instruments that could really measure the peak were particle detectors. And so there is some uncertainty to actually how you measure that. It was bright enough that it caused some atmospheric disturbances here on Earth. And you can see this really remarkable sort of 8-second periodicity in the X-ray emission that shows up that's actually due to the spin period of this highly magnetized star going off. So these giant flares are bright enough, they release enough energy, almost 10 to the 47 ergs, in a relatively short time span, that we should be able to see them out to tens of megaparsecs. So these could be that some fraction of what we call short gamma ray bursts are actually giant flares from relatively nearby galaxies. We don't have a great and compelling example of this yet. There hasn't been another one of these giant flares in our galaxy recently, but there's been a lot of magnetar science that Swift has been doing, both on the giant flares and even the sort of more basic ones. 2 in our galaxy, 1 in the Large Magellanic Cloud. Those are the ones that have had these giant bursts. Thank you. I mentioned shock breakout very briefly, but one of the really interesting discoveries from Swift was back in 2008. The shock breakout signal is the earliest electromagnetic signal following the core collapse or following any kind of sort of stellar explosion. Initially, you have this material that's optically thick and the photons can't get out. And eventually it expands, the optical depth drops, and you can then see the event. This is the sort of shock breakout from core collapse supernovae. In this one case, it was serendipitously discovered while monitoring this relatively nearby galaxy, NGC 2770, which had a different supernova in it. Supernova 2007 UY. You can't see it, the resolution on the projector, but there was another supernova that Swift was monitoring in this galaxy. It just happened to be taking UV images of that supernova when this tremendously bright X-ray flare went off. So this was completely serendipitous. X-ray luminosity of like 6 by 10 to the 43, a duration of a few hundred seconds. Again, this is actually kind of long for a shock breakout signal. If you think about the size of a typical massive star, you would expect the duration to be less than 100 seconds, maybe tens of seconds. Again, this might be telling us that these stars, before they explode, are shedding a lot of material prior to their explosion. And then, it turned into a relatively normal type 1b supernova. This is a pretty interesting way for us to study the progenitors of the systems. And there are a number of wide field X-ray missions that are being proposed now that could detect these shock breakout signatures in much more reasonable numbers. Tidal disruption events. On the 28th of March in 2011, the Burst Alert telescope on Swift triggered on what it originally called GRB 110328, after the day on which it was discovered. But it quickly became clear that this event was not in any way like a normal gamma ray burst. On a normal gamma ray burst, you see an X-ray afterglow. It fades relatively quickly like this. That's what's shown in these black or sort of light curves of normal gamma ray burst afterglows. This thing was highly variable. We saw a variability timescales of 100 seconds. It would change by roughly a factor of 10 at X-rays, and extremely long-lived. So this was pumping out X-ray luminosity of like 10 to the 46 ergs per second for many months. So really incredible event. There was also radio emission associated with it. From the sort of basic synchrotron theory of this radio emission, could actually measure the size of the radio emitting region, use that to infer the presence of a newly formed sort of mildly relativistic jet. And we were able to pinpoint the location to the center of a galaxy that did not have an active galactic nucleus in it. And so the sort of picture that we put together for all this is what we call a relativistic tidal disruption event, where you have a star that wanders too close to a supermassive black hole. Its tidal forces, the difference in gravity between the front side of the star and back side of the star, can become stronger than the star's own self-gravity. It's torn apart. The accretion onto the supermassive black hole powers the resulting electromagnetic radiation. And in this case, it was actually able to form a relativistic jet, presumably due to something like the spin of the black hole, the magnetic field in the black hole region, some process that we don't completely understand. So Swift has made a number of discoveries using its high energy telescopes, the Burst Alert telescope, and in one case, the X-ray telescope, of transient high energy phenomena. But really what we spend the bulk of our time doing now is actually follow-up. So another space-based facility like Fermi, ground-based transient facilities that are discovering supernovae and other things will say, hey, Swift, we found something interesting at this point in the sky. It would be really powerful if we could get some ultraviolet and X-ray emission observations of these sources. And like I said, this is basically what we spend more than 50% of our time doing from the observing time perspective. So I wanted to go over just a few of these sort of discoveries, since I think some of these will be things that we're talking about here. This is observations of a young supernova. This is a type 1a supernova. So these are the kind that we use for cosmology to measure distances out in the universe. And you can see that most type 1a supernova observed at early times have relatively faint and rising ultraviolet emission, but this one shows relatively bright and fading ultraviolet emission. Now, we only caught it after a few days, so there's a little bit of uncertainty here. But what we think is going on is that this star ran into some kind of relatively large companion. And the shock heating from that interaction gives rise to ultraviolet emission that we can only observe for a few days. So this would be pretty compelling evidence of a single degenerate progenitor channel. So a white dwarf that is pulling material over from a main sequence or a giant star, rather than two white dwarfs that collide to produce a type 1a supernova. Now that doesn't tell you that all type 1a supernovae come from this progenitor channel, but at least for this one, I think that's pretty good evidence. I'm going to skip over this because we're running a little low on time. In addition to discovering tidal disruption events, this is something that we actively follow up on as well. Tidal disruption events that are found from X-ray surveys, from ground-based optical surveys. Here's one of the canonical examples from the Assassin survey, where we have a nice X-ray light curve out for almost a year in this event, very well sampled ultraviolet light curves. And in this work here by my former postdoc, DJ Pasham, he was able to measure a lag signal that the X-rays lagged behind the ultraviolet optical emission by a time scale of about 30 days. This is telling us, giving us an important clue about where the ultraviolet emission is coming from in these events. We've been doing a number of dedicated campaigns to do reverberation mapping of AGN. This is what these kind of light curves look like. So 6 of these filters are the ultraviolet optical telescope filters from the UVOT on Swift. A couple are different X-ray bands, and I think a few are some optical from some ground-based telescopes. By measuring the lag between all of these different bands, we can use these to constrain the size, the orientation, the geometry of the accretion disks in these systems. In particular, the few campaigns that we've done have suggested that these accretion disks are actually about a factor of 3 larger than standard sort of thin disk theory would predict. So that's a pretty interesting result. And we have been monitoring a number of novae. I don't think we're going to talk about this too much in this session here. This is a particularly interesting one. It has a recurrence time of a year. So we can actually pretty well predict when it's going to go off again. We know it to within a week or two. And so we can start our observing campaign actually before the nova turns on and measure the rise time, both in the UV and in the X-rays, which is completely sort of unheard of before. Because the recurrence time is so short, that requires a very massive white dwarf, something like the Chandrasekhar mass. So this is an interesting system when it comes to progenitors of type 1a supernovae. Where are we going in the future? We'll hear a lot about multi-messenger astronomy, LIGO and Virgo coming online with even more sensitivity, high-energy neutrino detectors. This is obviously going to be a very exciting field going forward. More ground-based transient surveys are coming online. We've had really good partnerships with the Assassin survey, with Pan-STARRS. We're excited about the Zwicky transient facility, 47 square degrees, which is just coming online now. And of course, LSST in a few years, which will be the proverbial fire hose. And we've been trying to sort of diversify a bit and started doing some more exoplanet work. So this isn't necessarily, this is somewhat a transient science. Measuring depths of transits at ultraviolet wavelengths can tell you something about the atmospheres of these planets. Looking for flares around low-mass stars can tell you something about habitability. And this is obviously something that is of great interest to astronomy as general, and so it's something we've been trying to push on in the last few years. So in my last slide, I just want to summarize a few sort of lessons learned looking back at the Swift mission 20 years after it was originally proposed. When it was first proposed to have a fast slewing, in particular autonomous spacecraft, people at NASA kind of freaked out. They were not really ready to handle something that could repoint automatically on its own. They thought it's not going to be safe. We have to do this on the ground. We have to do safety checks. The spacecraft vendor people that we talked to said there are military satellites that do this all the time. It's not like it's all that novel. And indeed, I think they were right. And now having something, particularly if you have a narrow field of view telescope, having something that's fast slewing, I would say, is almost kind of required. Even if you're not observing transients, just to do it so that you can observe efficiently, to me, seems to be the way you need to go for any spacecraft going forward. Having the opportunity to take risks, Swift was a GRB mission. We spend less than a quarter of our time doing GRB science now. I think that was really sort of one of the big legacies of Neil, is how to take scientific risks in a smart way, but in a way that can pay off tremendously. And we have a really amazing operations team and strong support from the community, and that has been totally critical for our longevity. So I will finish there. Thank you all very much, and happy to take any questions. Yair.
So I know it's hard to predict, but I was wondering, what is the outlook for Swift? I know there's lots of technical and political uncertainties, but if you could give us your personal pessimistic, realistic, and optimistic predictions about the Swift mission lifetime technical capabilities.
Sure. So there's no consumables on board. So there's nothing, there's no fuel that we're burning through that's going to limit us. The orbit is stable at least for another 7 years. And likely the sort of burn time would be sometime in the middle of the 2030s. So that's almost certainly not going to limit us either. So it's one of two things. It's either a question of funding, or it's a question of some kind of technical failure. If you look at missions like Swift, if they survive their first sort of month in orbit, typically they last for at least 10 years. Sometime between 10 and 20 years, the parts really weren't made to last that long. And so, I can't predict what it might be, but any of these things could be what gets you. There's nothing that we know of. There's nothing that we're tracking. The instruments degrade at a level of like 1 or 2% a year, so it's relatively modest. But either something like that or funding is what is going to do it. My expectation, we have the senior review coming up. We're submitting another proposal a little more for a year from now that will cover the period of 2020 to 2022. I think we'll be well positioned for that in terms strategically, in terms of advanced LIGO, Virgo, IceCube, variety of other science. Beyond that, it's hard to say. Speak.
Is there any other replacement mission with comparable capabilities which is on the drawing board or planned or?
So the closest replacement mission is the Chinese-French mission known as FOM. The last that I had heard, and this may not be totally up to date, so someone should correct me if I'm wrong, but I had heard that had been, launch date seemed to be settling down for sometime in 2022 or 2023. It has a similar sort of X-ray telescope with a comparable field of view. It's a little lower energies. It was designed more to do high redshift gamma ray bursts and less to do short gamma ray bursts. So it's a little lower energy. The predicted discovery rate is something like 70 GRBs a year. The nice thing is that it has an onboard telescope that goes farther to the red. UVOT cuts off at like 0.6 or 600 nanometers. This pushes out to 800 or 900 nanometers, so it'll be better for high redshift GRBs and afterglows. It has an onboard X-ray telescope, but it's not quite as sensitive. So it's comparable in a number of ways. And you'll hear from Krissa, I guess, in the next talk about mission concepts that NASA is working on for future transient missions.